Hi, everyone. Welcome to Chapter 6, which is entitled Atmosphere and Air Pollution. In this chapter, we will be describing the composition and structure of the atmosphere, explaining the importance of the ozone layer, the depletion of the ozone layer, and specific steps taken to address this problem. We will distinguish between indoor and outdoor air pollution and how these two types of pollution compare to industrialized countries versus less industrialized countries. We'll identify natural and anthropogenic, in other words, man made sources of air pollution. We'll explain the effects of air pollution on human health and the health of ecosystems. And finally, we'll look at the Clean Air Act, a piece of legislation here in the US that governs air pollution, and talk about the impacts that it has had on our air quality. So before we can get into these matters of air pollution, we need to talk about what air is and what the atmosphere is. The atmosphere is a thin layer of gases that we call air that envelops the Earth. The atmosphere is critical to maintaining Earth's systems and providing hospitable conditions for living things. It serves as a medium for heat and water vapor to be transported around the globe. It regulates the temperatures that we experience on the surface of the Earth, and we'll talk more about how the atmosphere does this in just a minute. It serves as the source of gaseous carbon dioxide and oxygen that are used by living things in their metabolic processes. And it shields the surface of the Earth from external threats like harmful cosmic radiation. And we'll also look at how this happens in just a moment. But before we do, a quick look at the composition of the atmosphere. We've talked about how the atmosphere is mostly made of nitrogen. 78% of the air particles floating around are molecular nitrogen, 21% are oxygen. Then every other component of air is pretty small compared to these two. Argon gas is the next largest at 0.9%, then carbon dioxide at 0.042%, and all other gaseous components bundled up together make up the remaining 0.058%. When it comes to understanding how the atmosphere performs some of its most important functions for Earth's systems, we have to look at the structure of the atmosphere because those functions are tied to the structure. So we think about the atmosphere as being divided into four different layers. The way that these layers are distinguished from each other is based on a number of their characteristics, including the temperature of the layer, the chemical composition, so what gases can be found in it, the way that those gases move or don't move throughout the layer, and the density of the layer. There's a gradient where layers that are closer to the Earth are more dense because the force of gravity pulls the air downward, and the air column stacks on top of itself. So we can imagine this compresses the air at the bottom of that air column. The lowermost layer of the atmosphere is called the troposphere. This layer extends from the surface of the Earth upward about 7 miles or 12 kilometers. Within the troposphere, air flows and swirls continuously, and that activity allows both moisture and heat to be distributed across the planet. And this also plays a role in weather events because the troposphere is where weather takes place. And the continuous movement of gases in the troposphere is tied to the temperature gradient that is observed within this layer. As you move upward in the troposphere, the temperature decreases and gets colder. In this illustration on the right, that's where the yellow line is showing temperature. Temperature is represented on the horizontal x-axis. So you can see as you move upward, the temperature drops. At the Earth's surface, the average ambient air temperature is about 20 degrees Celsius, about 18 to 20, or 68 degrees Fahrenheit. But at the top of the troposphere, it is negative 55 degrees Celsius or negative 67 degrees Fahrenheit. So, why is this the case? Well, solar energy, also known as solar radiation, is what causes our planet to be warm. Remember from our previous chapters, the sun is the only source of new energy coming into the Earth's system. So the solar radiation hits the Earth and causes the ocean and the land to warm. Then, like any object that has been warmed, the water and land give off some of that heat. And because the lower levels of the troposphere are closest to the Earth's surface, this is where the largest amount of emitted heat is concentrated, and therefore the surface of the Earth is where you find the highest temperatures in the troposphere, with things getting cooler as you go higher. Some of the solar energy that the Earth gives off gets released back into space, but a lot of it is retained because the gases in the atmosphere that are referred to as greenhouse gases, leading to the greenhouse effect. The greenhouse effect is the phenomenon where heat that is given off by the Earth gets trapped in the atmosphere by certain gases, which of course causes temperature in the atmosphere to increase. The short version of this explanation is that certain chemicals in the air block the heat, certain chemicals in the air block the heat that Earth has absorbed from the sun from escaping out into space. And this contributes to overall higher temperatures in the troposphere. And on the Earth's surface, we'll talk more about the greenhouse effect in our next chapter on climate. But now that we understand why this temperature gradient exists in this troposphere, with the lower part being hotter and the upper part being colder, we can address how this contribution to the movement and flow of air, how this contributes to the movement of, and flow of air within the troposphere. In the troposphere, you get these things called convection cells, which are areas where warm air is ascending and cool air is descending in a circular pattern. The reason for this phenomenon gets back to principles that we learned in a previous chapter about how temperature works. Remember that temperature is a measurement of kinetic energy, and kinetic energy is the energy of movement. So higher temperature means more molecular movement. Gaseous particles that are found lower in the troposphere pick up more heat energy that is being given off from the Earth, and therefore they are hotter and move faster. This extra kinetic energy means that they are spread out more and become less dense, which causes them to rise upward. Remember, dense things float on more dense things. Then, when the particles get to the top of the troposphere, it's cooler up there, so they cool down too. With less kinetic energy, their molecules move slower, and because they're not bouncing around so frantically, they occupy less space and become more dense, and this causes the cooler air to sink. The result in this continuous movement of air in this circular pattern, and this pattern contributes to what we know casually as wind. Wind is the movement of air from areas that are referred to as high pressure areas, because the air is more dense, to low pressure areas, where the air is less dense. Wind is part of our sporadic weather patterns, but there are also big trends in wind patterns and how wind occurs across the globe. One example of a particularly important wind pattern is referred to as Hadley cells, which is what is being shown in this diagram here. So this blue blob is sort of a cutout of one small part of the Earth, with the equator being shown in the middle line at 0 degrees latitude. And then on either side of the equator, the diagram goes up to about 30 degrees north and 30 degrees south to the bottom. So Hadley cells are the result of the fact that the Earth is heated more intensely at the equator, which causes warm, moist air with high humidity to ascend higher into the troposphere at the equatorial regions around 0 degrees latitude. The water vapor that the ascending air brought with it contributes to precipitation, making these regions around the equator very wet. But then at the top of the troposphere, the air cools. It's now very dry because it's lost its water vapor. And then it descends back down at about 30 degrees north and 30 degrees south of the equator. And this influx of dry air at 30 degrees north and south of the equator contributes to a pattern where deserts are more likely to occur at 30 degrees north and south of the equator, but we'll talk more about that when we get into biomes. For now, let's get back to the structure of the atmosphere. So we've seen the characteristics that define the troposphere. At the top of the troposphere is a barrier. That is referred to as the tropopause. The tropopause is a boundary where the temperatures stop increasing as you go up. And in fact, the opposite starts to happen as you continue into the next layer. As we will see in just a minute, the reason why this occurs is because at this point, you hit something called the ozone layer as you're going to get into the stratosphere. Stratosphere is a layer just above the troposphere. It extends from the top of the troposphere at about 7 miles above the Earth's surface up to 31 to 33 miles. And the stratosphere composition is distinguished from the troposphere in a few ways. One of these is that the stratosphere contains almost no water vapor, and another is that it contains approximately 1,000 times more of a chemical called ozone, which we will talk about extensively in our next section of this chapter. But for our purposes here, all you need to know is that ozone is a chemical that absorbs much of the harmful radiation from the sun, specifically UV radiation or ultraviolet radiation. The sun actually produces three different types of UV radiation: UVA, UVB, and UVC. The ozone layer absorbs and captures all of the UVC and 90 to 95% of the UVB. So, in that sense, it provides a protective shield and is also uniquely susceptible to warming because it absorbs this UV radiation so well. Because of this, the temperature gradient that you see in the stratosphere is the opposite of what is seen in the troposphere. In the troposphere, as you went up, things got colder. In the stratosphere, as you go up, things get hotter. So, in our figure at the right, if we follow the yellow line, we can see that the temperature increases as you go up. This is because the upper part of the stratosphere gets more exposure to solar radiation, and so it heats more readily compared to the lower layers. As a result, the hot air is already at the uppermost layer of the stratosphere, and so you don't get the occurrence of the convection cells of circulating air that you see in the troposphere, and the air is relatively calm with little mixing. And one note that needs to be said here is yes, it is getting warmer, but the air is thinner. So there's not as much air to warm things up in the atmosphere. So if you were to be in the stratosphere, it would feel rather cold because there wouldn't be a lot of air particles around to warm your skin or the transfer heat to your body. But those air particles themselves are warmer. Then, moving upward from there, the upper boundary of the stratosphere is called the stratopause. And then past the stratopause, the next layer is called the mesosphere. This layer extends from the top of the stratosphere, which remember is 31 to 33 miles from the surface of the Earth, up about another 20 miles to 53 miles above the surface of the Earth. One thing that distinguishes the mesosphere from the stratosphere is its lack of ozone, and therefore, because it lacks this chemical component that so readily absorbs the UV radiation, the temperature gradient again looks more like the troposphere. The temperature decreases as you go higher because the lower levels are adjacent to the hottest part of the stratosphere and are catching all of that energy that is being emitted. Then the top boundary of the mesosphere is called the mesopause. And then finally, the highest layer of the atmosphere is called the thermosphere. This is considered to reach all the way up from 53 miles above the surface to 373 miles above the surface. So a much bigger area than the other layers. The thermosphere has an extremely low density of air, and its temperature gradient looks like the one that we saw in the stratosphere. As you go up, the temperature increases. This is because this layer is just so exposed to the sun that the highest particles capture the most heat. At the highest parts of the thermosphere, the temperature of the individual air particles can reach 2000 degrees Celsius, which is 3600 degrees Fahrenheit. However, an interesting fact about the thermosphere is that because the density of the air particles is so low, it would still feel incredibly cold because the air particles are so sparse that you wouldn't be able to perceive the heat they are carrying.